Hello everyone. Welcome to lecture 4 of this GAN lecture series. To recap what we have been discussing in the previous class, we talked about the diffraction of light, and whenever you have an object at the small scale which has, then you can see this like blurring of the edges here. This is because of diffraction, and the ray optics picture does not tell us why this is the case, but the wave optics picture does. And we will explore this in much greater detail as to why this blur is and how to quantify it and so on. The other thing that we discussed last time was where the Fresnel and Fraunhofer diffraction, the concepts of Fresnel and Fraunhofer diffraction. To summarize, basically, in like if you have a point emitter of light, uh, as you go a certain distance away from the source, in a certain region, you can make a what's called a parabolic assumption about the nature of the wavefront. And if you go still further, you can think of it as plane waves. As this one dot will become a plane wave. So the first one is the Fresnel approximation, and the planar one is the Fraunhofer approximation. So we'll continue with these two ideas and look at how this affects imaging systems. So we'll go into the details of microscopy and so on in today's lecture. So I'll start with when you have a single lens, and we have an object kept in front of a lens at a distance b1, and it has a focal length f, and you have an image plane at a distance d2. Then you know that if 1 over d1 plus 1 over d2 minus 1 over f, we call this epsilon in today's lecture. If this is equal to 0, then the image will be a replica of the object with some magnification and inversion. So this is, you probably have seen this from your high school or 11th and 12th. So this is also true in the ray optics picture. Now an important question is, what happens if you put a screen not in the image plane but little up, a little further closer or a little farther away? Then what do you see? What do you expect to see? And how do you understand like what happens in that case? That's the next question we will explore. Okay, so here is kind of, if you just have one point emitter and you have a lens here, and you have like basically there's a limit to which the light rays, like there's a limitation. You have what's called an aperture. Basically, you take a black piece of paper, cut a hole in it, and put it in front of it, and so light here is getting blocked. Only light in the middle is going through. Then what do you see? If you are at this point, which is the image plane, then you see a dot in the ray picture of light. But if you move the screen closer here, what you see is basically like a circle. So if you take a cross section, it looks something like this. So basically, there's a circle, and the circle becomes bigger and bigger as you come closer. That's the kind of intuitive picture you have if you use ray optics of light to understand this. Okay, so that's why you have defined this 1 over d1 plus 1 over d2 minus 1 over f. If this is equal to 0, you are at this plane. But if you are not at 0, then epsilon tells you how much away from the focal, like the image plane you are, and that this is the parameter that quantifies that idea. Okay. The next important thing is, from the previous class, I told you that if you have a lens and if you put an object at a distance f away from that lens, and if you put the image plane at on the other side at a distance f, then this plane is the Fourier transform of this plane, right? That was an important result that we got in the previous class. Now, it turns out that using this idea, we can construct fairly complex imaging systems like microscopes and stuff. And that's basically the topic for the first half of lecture. How exactly to do that? What you can in some ways, one way to think about this is, take a object which you want to kind of get an image of, put it in front of a lens at a distance f. In this at another distance f, you have some kind of this will be the Fourier, what's called the Fourier plane. So this plane is a optical Fourier transform of this object. Okay, whatever light is coming from here, take the Fourier two-dimensional Fourier transform. That will be including the complex numbers. It's not a real. It's complex. It's a complex Fourier plane here. And then if you do it again, put another lens here, and this pair of Fourier, like this pair of f and f, will give you another Fourier transform. What is the Fourier transform of a Fourier transform? Anyone wants to guess? Yeah, sorry, can you say that again? It's okay, you can guess. If you are wrong, it's okay. Yeah. It's inverse, not quite. Say you take a Fourier transform of something, and then take the Fourier transform again. If sorry? It's the same, but there is a subtle difference. You wanted to say that. It will be, okay, it will be almost the same as the original quantity except for minus sign. It will be an inverted minus, basically Fourier transform, and then you take the inverse Fourier transform, you get the exact same object. You take the Fourier transform and then again a Fourier transform. What's the difference between a Fourier transform and an inverse Fourier transform? There's a minus sign, right? That's about it. In the minus one in one, the thing is e to the plus j 2 pi mu t, and other case it will be e to the minus j2 minus, instead of plus it will be a minus. And the forward inverse and the forward. So basically, what it means for us in optics is that you have an object, take a Fourier transform again, you get the inverted object over here. That's it. Okay. So everything is self-consistent. So you get the minus. You just flip it down. That's what up becomes down. That's what you actually see if you put a screen there. Now, what's the mechanism? It looks like you're replicating, like after putting two lenses, you just made a copy which is the inverse. What's the point? The point is that this Fourier plane is very, very useful. You can manipulate in the Fourier domain, you can manipulate the image in such a way that you can kind of make it look however you want. What can you do? I'll do that in the next few slides. But the important thing is you have control over the Fourier coefficients. So imagine like you have in a one-dimensional case, you have a signal, you compute the Fourier transform, then you can do some filtering, right? You can remove high frequencies, you can remove low frequencies, you can do some kind of filtering process, and then you can take the inverse Fourier transform, and then you can change the signal. That's kind of an image like signal processing system, right? That's what you do. This is an optical version of that, optical analog of essentially that. You have this gives you control over the Fourier coefficient of your image, and what we can do is kind of limited by our imagination, and the smart people have figured out what to do with this, and that's something I'll talk about. This kind of a system is called the 4F imaging system, because this is a distance f, there is one more f, another f, and another f, 4f. There are four like focal lengths essentially in this kind of a system, and so it's called a 4F system. If you have the letter f here as the object, shine light on it, it will get Fourier coefficients of f here, and then if you put another lens, you'll get an inverted image of f on the, if you put a screen or a detector, a camera sensor over there, for example. Okay, that's basically this is a fundamental and an important idea, and the crucial piece here is that h of nu, this here is the transfer. So to go back to this figure, so h of nu x to y in the Fourier plane. So this, let's say you can put some kind of a screen, or like how do you do any kind of filtering? You can put some kind of a screen. Maybe if you, so in this case you can, if you want to remove the high spatial frequencies, you can put like something which literally physically blocks off high frequencies. If you want to keep remove low frequencies, you can put something which removes the low frequencies, or you can do like any kind of a filter. In general, it can be like some kind of a transparency which has some pattern on it, which keeps some frequencies and removes other frequencies. That's essentially like sort of, this is, you can think of this as a two-dimensional filter which transmits some frequencies and keeps some frequencies, and the transfer function is basically equal, like is equal to this function p of like in this domain. Does this make sense? Any questions? This is a crucial concept. This is analogous to, like, basically this allows us to use everything that you've learned in any kind of signal processing or class in the field of optics and instrumentation. Okay, this idea of like a Fourier transform using a lens, okay, a pair of lenses. So I wanted to bring kind of connect these things to like how it is relevant to like building instruments. So what we are talking about in terms of the properties of waves and properties of lenses and so on is something you have probably seen in physics. And so physics, so we are in an engineering institution. So what is the difference, or what is the connection between engineering and physics? So physics tells you the principles of how some nature works. And as engineers, what we do is take those principles, connect them to some other ideas, and build something which can use in the real world. So in order to build something new and interesting and something novel, which build a new kind of an instrument, you need to first understand the principles. If you can understand the principles, that's say the physics principles, then you need to figure out how this is useful in the problem that you're solving. If you're trying to solve it, like make an instrument which does something, then basically if you can understand exactly what it does, then you can use it to make a new system. In fact, in the next few slides, I'll show you exactly, give you one example of what I mean by that. Okay. So yeah, that's yeah. So this is kind of a 4F image system. In order to control the Fourier frequencies, we can put what's called a mask. Mask is basically like, could be something like a transparent object where you have something printed on it, or some like some part of it is blacked out, some part of it is like kind of let light through. So you can take for example, you can take a piece of paper, cut a hole in it, and this part blocks light. The light only goes through the small region, and you put this over here. That's an example of what you could do. Okay. So now, if you take an object, and let's say the Fourier transform has some particular shape. Okay. Now, if you only keep these frequencies, or other. Sorry, can you hear me properly? Okay. So if these other frequencies and keep the low frequencies, and what you think will happen intuitively, you don't need to give me a mathematical expression or something. Intuitively, what do you think should happen to the image? In other words, let me actually show you a picture. Okay, I'll get back to this. Okay, so I have an object, I have a mask, I put this in this location over here, which keeps low frequencies and removes high frequencies. What do you think you will get as the output on the screen? Any guesses? Sorry? Only noise? Not quite. You'll see something about you'll get some something like an image, but not quite. So you will not get pure noise. Any other guesses? Some frequencies are being removed. Therefore, what will it do to the image intuitively? Correct. What do you mean by that? The quality will be worse than before, but what, like, in what way will it be worse? Correct. Edges will be blurry because edges correspond to high frequency components, and if you remove high frequencies, it will make it blurry. That's the basic intuition, which is correct. In fact, if you look at an image, it will look something like this. Okay, a relatively sharp image. You put the mask in the Fourier plane, it will look essentially something like this. Okay, so here is, yeah, so basically image will be take the object and multiply. So basically it's there's a transfer function, and the transfer function is the mask over here. And if you like, so basically if of all the frequencies present, if you remove the high frequencies and keep the low frequencies, it will make the image look blurry. Okay, that's the crucial idea. What happens instead of take the same image, so it blocks off the low frequencies and lets all the higher frequencies through. Now what do you think you will see? Yes. Any guesses about what happens next in this situation? Sorry? More contrast? In what? More contrast in some way, yes. In what way? Say that again. Clarity. You're on the right track, but there is a subtle thing which is missing. Yeah. Yes, edges will become more prominent because the edge, it keeps the high frequencies. The edges will like will be edges, but the other things are, so in relative terms, the edges will become much more prominent. So in fact, that's exactly what you will see. You can see that the edges, like here is blurry, here the edges have become more prominent, right? That's in fact exactly what you would expect, what you will. So it's basically low pass filtering in one case, which is the first one. High pass filtering, if you like do in the course on image processing, you will actually see that this is exactly what like you can actually do this computationally, but we are doing this in a microscopy imaging kind of a system. Okay, let me give you a third example. Let's say you have a grid. What exactly is this? So basically, you take like transparency of some sort and draw lines on this. Okay, something of this sort. Okay, so now if you have very few lines, then it is like basically it's low when you have, sorry, let me draw it here. If you have very few lines, this is low frequency. When you have a lot of lines, it's high frequency along this dimension, right? And if you have a few lines like this, it's low frequency along this direction. If you have a lot of lines like this, it's high frequency along the horizontal direction, right? You get what I'm saying? So these are what are called spatial frequencies. So spatial frequencies along like this vertical direction, spatial frequencies along horizontal direction. So now the question is, if you have a combination of high frequencies this way and this way, and you put a mask which looks like this, what exactly is this mask? What do you think it does? There's some kind of a filter. What kind of a filter is it, or what does it do? You can guess. This is not like you're seeing it only for the first time, so it may not be obvious what exactly is happening. So what do you think is happening? And so this is like a slit of some sort, right? Like, so basically, it's kind of it's letting all these Fourier coefficients this way through. It's blocking some here and here. So intuitively, if you give it an object, what is it doing to the object? kind of, but think in the frequency domain. So what frequencies is it letting through and what frequencies is it keeping? Sorry, you said something? You're on the right track. So the thing is, it's so this unlike here where it's a circularly symmetric, here it is different along x direction and the y direction. So if you look at the horizontal direction, it's a low pass filter along the horizontal axis. If you literally like draw a line like this, it looks something like this, right? It's keeping low frequencies, removing high frequencies. So horizontally, it's a low pass filter. Vertically, if you draw a line like this, draw a line vertically like this, so it will be like essentially it allows all frequencies to go through. So it does not do anything along the vertical direction, but it does low pass filtering along the horizontal direction. That's the nature of this filter. Does everyone first understand this? So it's on one axis, it's a two-dimensional Fourier transform, a two-dimensional processing. So along the horizontal direction, it does low-pass filtering. Okay, and along the vertical direction, it keeps everything that is there as before. Okay, and therefore, if you think of that and apply that to this image, what do you think intuitively you should see over here? What do you guess as the result of this kind of? That's a very good guess. Yes. Anyone else? You're on the right track, but there is a subtlety. Okay. Anyone else wants to guess? You will see horizontal lines. You will not see vertical lines. It's kind of the reverse, like there is XY confusion a little bit. So I'll tell you why. So along the vertical axis, so all these, so the spatial frequencies which are like this is the vertical axis. It will keep all of them. So this is kind of like high frequency along the vertical axis. Along the horizontal axis, previously it was like this, and because this is high frequency, it's just getting removed. So basically, these sorry, yeah, these frequencies are essentially getting removed. So it's removing the like frequencies which were along this direction, the lines which were along this direction, the vertical lines. So like the vertical lines horizontal axis. So these are along. So this corresponds to the spatial frequencies along the horizontal. The lines are up and down, but the frequency is corresponding to this horizontal. That's a subtle thing which is not intuitively obvious, but that's something you must keep in mind. Vertical axis. Okay, so the lines I've shown, the left to right lines correspond to the vertical frequencies. Okay, these lines correspond to the horizontal frequencies, and we are removing these lines from like these lines, and we are only keeping this. So basically, we get only lines which are like horizontal in nature. Okay, so that's the nature of this 4F imaging system. Okay, so the basic idea I want to convey to you is that we have this physical phenomenon where you take an object, put it in front of a lens, you get a Fourier transform. You can do anything you want to do in the Fourier domain. You can kind of keep some frequencies, remove some frequencies, do whatever you want in that frequency domain, and then you can again take a Fourier transform and you can get an image on the other side. So it allows you to control Fourier domain. So what's the point? What is it that you can do with this as an engineer? If you want to build something which is useful, what do you do? The answer, one of the first answers, were a scientist by the name Zernike. Zernike came up with an idea where what he did was basically took a lens, took the Fourier domain here. Sorry, it's a bit blurry. Yeah. So, and then he put just a small piece of glass in the very right in the middle. Okay. And what it does is adds a constant to the image. Okay. So, let's say you have an like object which is a purely face object. Like the face, all the information that is there is in the face. And what kind of an object it is, I'll get to that in just a minute. But let's say there is an object which is practically transparent, except for there is it has a face. What is the face? It has like some kind of a height profile of some sort. Like it's a glass where there is like glass or like some kind of an object where it has a, let's say for example, so a classic example of something of this sort is like a bacterial cell or some kind of a cell. So I don't know if you know this, but in biology, most cells are actually transparent. Can you see? Yes, maybe I'll draw in green if you like. Okay. So in biology, most put something on a slide or a petri dish and look at most cells. Really transparent. Inside the human body, the cells you think are red or some color of that sort, right? That's because there is actually blood, and there is some scattering. But if you actually take a single cell and grow it on a petri dish, most cells are almost transparent. They don't have, you actually have to add colors to see them. Otherwise you can't see, typically you cannot see. So biologists, since the invention of a microscope, could not see living cells. If you try to put some chemical on it to make the color something which is not what it is, like so normally cells don't have a color. So if you look at it under a microscope, you literally see nothing. In fact, what you see is something of this sort. Okay. So as you like, so this happens to be a nerve cell or a neuron. Okay. So if you grow a cell in a petri dish or something like that, if you look at it under a microscope, you literally see almost nothing. Right. So now, and if you want to see the cell, previously people used to put some chemical like a color, like a dye or a stain or a fluoro or something of that sort, which basically a chemical, it changes color and it attaches to the different parts of the cell and it shows a color. But the process of putting this chemical usually kills the cell. At least 100 years ago, that was a problem. And so you could not really study living cells under a microscope. Okay, so that was a crucial kind of problem in biology. It was very hard to solve at that time, even though microscopes had been there for more than a couple of 100 years by that time. But nobody knew how to see living things, living cells under a microscope. So what Zernike did was he thought of it as an engineer, he modeled it as basically a face object. Like so, the problem is that the shape of the object is encoded in the face, and so the equation for that is something of this sort: e to the I phi of x comma y. So phi is where the shape of the object is in here. So if you take e to the I phi, if you take the magnitude, so what is the process of measurement when you have the field here? What is the intensity of xy? I told you last time is u of xy squared, right? And if this is e to the I phi of xy. So what happens when you take magnitude square of a complex number? What is this? Sorry? It's not pi square, no. E to the I phi. What is the magnitude of e to the I phi? Sorry? It's constant, it's 1. Right? E to the magnitude of e to the I phi is 1. Right? So basically what you see is 1 which is like basically a flat nothing, just white everywhere. That's actually what you see here, right? This is just basically like white everywhere. Therefore what it means is this is a face object where when you make a intensity measurement, when you look at photodetector and see what it is, you will see nothing. You will see 1 constant, like almost like nothing, right? So that is the problem. What he did was basically in the Fourier domain, you add a constant to the DC term. DC is the middle, the very middle, right? You put a piece of glass, do something there, which will add 1 to this. Okay? Sounds simple. Just add 1. In physically, how do you do it? Think in the Fourier optics method, using the idea of Fourier optics. In the Fourier plane, put a piece of glass just in the right place of the right thickness. Okay? Then what you see is this. What is happening? What happens when you do this? In fact, so when you take the magnitude square of this, what happens? So now, so if you take 1 plus e to the I phi, take the magnitude square, then what happens? 1 plus 2 e to the I phi, right? So there is, this phi is not lost. And if you take the real part, it will be cosine of phi, something related to cosine. So the phase is no longer lost when you take the magnitude square. So what it means, we'll get to the little more details a little bit later. But the basic idea is that what looked like almost like nothing, a washed out image, will look so much clearer with this idea of like kind of, and so this is in fact the kind of thing that even today we do, like in my lab or in most optics and instrumentation labs. Like sort of you try to figure out some clever way, do some small thing in the experiment you build, like put 4 lenses, put few things, do some kind of build a system. You make this small change, what looks like a small change, but it's really not. Like it's a profound change. It's based on a deep understanding of physics and engineering and so on. So what you do is convert this image into this image, and so this gives you a contrast which is proportional to the phase phi of xy, the phase of the object. So this allows you to get an image of what was previously not possible. You can get a good image of a cell with this. So this is called phase contrast microscopy. So he invented a new kind of mechanism to see living cells, which was very hard to do before that. And without adding any chemicals or other contrast agents. And this is like, in fact, after that, people could start seeing living things, living cells, for example, biologists and people in medicine. What's the advantage of that? They could, like, it opened up a whole new world of, like, imagine if you can only see dead things before, and now you can also see cells grow, like how 2 neurons connect with each other, how neuronal connections form, how kind of cells grow, how they multiply, how one cell becomes another cell, like all these things that could previously people could not study. Now you could really study under a microscope, and it opened up like sort of so many thousands of discoveries were made as a consequence of this invention. Okay, this was so important. So this was discovered in the 1930s or so, and for this idea, Fritz Zwicky got the Nobel Prize in 1953. So this turns out to be so important. You can see, and so this is the kind of microscope. This is in fact like quite often used in like practically every biologist, most biology labs have some version of this if they are interested in doing like sort of seeing transparent objects. Okay, so so what I'm trying to tell you is the physics principles that we learned in terms of RF imaging system. If you are clever and if you can use it for something, you can build an instrument which is this kind of an instrument which takes an image which was previously like this and makes it look like this, and which happens to be very useful, and it opens up like the world of possibilities for other scientists and people in medicine and biology can use it and do something useful with it. Okay, as engineers, this is the kind of thing which we hope to do for all the kinds of imaging systems. I'll give you more and more examples of this sort as we go along, but this is essentially this is what is the connection between all the things that we've been talking in the past few classes and kind of the practical real world applications. Okay, any questions about all this? Sure, yeah. So basically, if you like, so think of the 4S system here, right? So if like, in fact, in this example that I showed you here, so you block some, like you're blocking out the low frequencies, right? Make it very, very tiny, small. The smallest thing you can block is just the DC alone. Instead of all the low frequencies, the lowest possible frequency is the DC, right? The zero frequency. So the zero frequency, instead of removing it, add a constant to it. A piece of glass essentially delays the light. And like if you do work out the math, we'll actually work out a little bit of the math in a different slide in today's class. But basically, if you just add, like you're essentially adding like something, some number, like phase delay to the DC component alone in this kind of a system. Okay, that's the idea. Yeah. It may not be exactly one, but like sort of by choosing the right refractive index and thickness and some other things, you could choose what phase delay you introduce to the PC relative to everything else. Yeah. Any other questions? Okay. Okay. So let me get back to like, so we took like the 4S system. The next thing, a big topic I wanted to cover is that of resolution, and what is the meaning of resolution? What is, why is it kind of, how does it come about, and why is it that something looks blurry, and under what conditions, and what is the kind of this blur? What is the nature of this blur, and so on. So that's the next kind of topic I wanted to address. So let's just look at a single lens. So you have an object. In fact, in this case, I'm starting with something very simple, which is literally a point object which is emitting light in all directions. It's going towards this lens, and you put just a screen, like basically what's called an aperture here. So what is an aperture? As I think I mentioned this before, some, like say, you could buy an aperture where like a variable size aperture in optics. You can there are a lot of companies which can do that, but like think of it as a black piece of paper or metal where you cut a hole in it, and the size of the hole is something you can choose whatever size you like. Okay, so that's an aperture. It allows like only that amount of light to go through. Okay, even in DSLR cameras or something, you can adjust the aperture, right? You can adjust how much light goes through. Those of you who have done any photography can know what an aperture is. Like you can open and close an aperture, for example. So it's the same basic idea. Okay, so you have a lens in this plane, and then that light focuses onto screen over here. It's called the image plane here. Okay, so the light emitted by this object here is basically, we have seen this in the previous class, right? So it emits a spherical wave, and as it travels, it has this under the Fresnel approximation, you basically have this kind of e to the jx square plus y square kind of a formulation. So it's like it's a plane wave, or sorry, it's a paraboloidal wave hitting the lens. And what does the lens do? It changes the shape of the wave and focuses it onto a dot. Okay, so how do you? The question is, we'll figure out what is the relationship between this dot and what you see on this plane at any given location. So that's where we are going. So the first thing I wanted to kind of give you an intuition for is, what exactly does a lens do? We need an equation for what the lens does. So let's try to intuitively figure it out. Okay, so one good way to think about a lens is that, let's say you have a plane wave coming in, just flat plane wave. What a lens does is takes this and converts it into something which focuses onto a dot. Okay, So what does this mean? So this way. Oh, I see the problem. Okay, so like you can see this. So light is coming this way and it focuses this way. You can also think in reverse. So like there is in optics, if light goes in one direction, there is something called the principle of reciprocity, meaning if you like light comes from the other direction, it will follow the same path as it was like it had come from. Okay, if a point source is here and it emits light, it will follow this and it will go in the reverse direction. So it's basically like it's reciprocal. It's whatever how the shape in which it goes forward is the shape in which it comes back essentially. Okay. So now, why is this important? So what a lens does in effect is, if you put a lens here, it takes something, what is instant, it is basically a flat, it's a constant. What is constant? It will make it a parabolic shape. So it will make a, I'll call it spherical for now, but you know the shape I'm talking about. So it will take a plane wave and convert it into a spherical wave, and the spherical wave will converge to a dot. Okay? So basically, in other words, it takes the plane wave, it delays in the middle, it delays it a lot. In the edges, it delays it a lot less. So basically, it will take the curvature here, which is flat, it will take this curvature and converts it to this curvature. So therefore, it delays it a lot here. It delays, it delays it, this is a lot of delay. This is just a little bit of delay. So basically, at every point along this direction, it delays it by some amount. Okay, that's essentially what a lens does. So what is in the middle? There's a thick piece of glass. Therefore, it delays it a lot. What is on the edges? It delays it just a little bit. So the result is that take the plane wave and add something of the form e to the minus j x square plus y square. What a lens does is introduces something of the form e to the j x square plus y square by something of this sort. So it takes a plane wave and converts it into a parabolic wave. And that's really what a lens does. So mathematically speaking, takes a constant and multiplies it by this wavefront, of a wavefront which has the e to the x square plus y square. And if this propagates, and if that propagates, it will reach, as it reaches the other side, it becomes a dot. Okay, so if you make a wavefront which is this shape, if it propagates, it slowly comes down and down here, and it gets to the dot. So that's essentially. So in other words, what the lens does is introduces an equation of this sort. So it takes the light that comes in. So light here. So let's start with what's happening here. The field in this location, the field in this just before it enters the pupil, is a point source emitted, like it's traveling. The wave is traveling here, and so the equation for this surface, like the wave here, is e to the j x square plus y square. We saw this in the previous class, right? So this is basically the spherical wave hitting the lens. And once so take the spherical wave, it hits the lens. When it hits the lens, passing through the lens is equivalent to multiplying by this e to the x square plus y square by 2f equation. So in other words, it changes the phase from flat to a curved. If it is already curved, it could make it flat or further curved. So basically, it's taking the phase of light and shaping it in this particular way. That's essentially what a lens does. So in the wave optics picture of looking at things, a lens is something which does a phase transformation. It takes the phase of the light and multiplies it by this e to the jx square plus y square kind of equation. And then what else does it do? The pupil, the aperture here is equivalent to multiplying by p of x comma y. So just light just after it goes through the lens has this u1 of x equation. And how do you find the lens light over here h? Take this and convolve it with the free space propagation kernel. We saw this in the previous class. If you do this, you will get the point or the shape of the shape of what you will see on this plane. So you started with a dot. It goes through a pupil aperture and it goes through a lens, and you focus onto a dot. We want to find the shape of this. What do you see on this in this plane? And that will be this h of xy is what you will see on the screen if you put a screen or a detector over here. So, any questions? So you have an object, propagate it once to the lens, apply what the lens does, then propagate again to the screen. That's the essence of what we are doing. Okay. And so if you actually do this kind of solve this equation, solve this kind of, but it looks like a complicated equation, but remember that, okay, a mathematical aside, what is e to the j x square? What does this remind you of? Yeah? Does it remind you of some equation of some sort? Okay, maybe start with something simpler. E to the minus x square. What is this? What function is this? Sorry? It's a Gaussian. Correct. E to the j x square is a complex Gaussian. Right? You could have some sigmas that constant, but crucial thing is it's a complex Gaussian. E to the minus j x square plus y square by 2 sigma square, just as an example, is a complex Gaussian in 2 dimensions. So it's a Gaussian. So what we are essentially doing is taking a Gaussian, and in the previous class we saw that this, if you simplify it, becomes a Fourier transform. And so we are taking the Fourier transform for complex Gaussian. So these integrals are actually, it turns out to be, you don't actually calculate integrals, you just look up a table of Fourier transforms. Fourier transform of Gaussian is a Gaussian, you write it, okay? And that way you get this equation, okay? So basically, what you see on the screen, if you have a dot and a lens in front of it, is something of this sort. And so this, so this is the Fourier transform of this, like the pupil along with the e to the x square plus y square, what's called a generalized pupil function. So the reason this is important is we started with a dot and it goes through a lens and an aperture, and you see some shape over here. It's related to the Fourier transform of the obscuration, the pupil over here. That's the crucial idea that I'm trying to convey to you. So what you see here depends on how big this aperture is, how small the aperture is, and it's related to the Fourier transform of this particular aperture in this case. And in what you actually see is basically, if this, under the approximation that x square plus y square is divided by lambda d is small, then you just have the pupil alone, the aperture alone, which makes all the difference. And the reason this is important is like what you see on the screen is a Fourier transform of the circular aperture. So let's take a step back and think about in the ray optics picture. Let's say you have a dot. Okay, you put the lens in front, light goes like this, light rays go like this, they get focused. You will get a dot on the other side, right? That's the intuitively that's what you expect. A dot becomes a dot on the other side. What we are saying is in the wave optics picture, it's actually quite different. what is happening is that waves are coming like this, they get focused. The shape of this is not a dot. What is a dot in 2 dimensions? It's a delta function. So if you put a delta function as the input, you will not get a delta function as the output. You will get something else. What you get is the Fourier transform of the aperture over here. If you block the light, so in other words, yeah, let me get back to this. Yeah, so you will see a shape which is basically, so this is something like a 2-dimensional sinc function. So the aperture is basically like a 2-dimensional, if you take a rectangle function, spin it around circularly in a circular symmetric manner, you get aperture, right? If you take a square and rotate it along, you will get in 2 dimensions, you will get essentially like a this kind of circular hole or an aperture. So if you take the Fourier transform for rectangle function, what is it? Sinc function. So in 2 dimensions, it's a 2-dimensional, it's not a 2-dimensionally rotated one, but it's what's called a sinc function. So basically it's something like a sinc function in 2 dimensions, okay? So this is the shape of what you will see on the screen here. What is important about this? Counterintuitively, if you make the aperture very small, what happens to the width of this sinc function? If you make the rectangle small, what would happen to the, if you squeeze in the spatial domain, time domain, what happens in the Fourier domain? Sorry? It becomes broader, it expands in the Fourier domain. If you make it small in the spatial domain, it becomes bigger in the Fourier domain, right? And if you make it bigger in the spatial time domain, it becomes much smaller and narrower in the Fourier domain. That's the Fourier duality property, right? If there's one domain, if you have some like rectangle, if you make it smaller, it becomes bigger in the other domain. So that's exactly what happens here. If you make the aperture small, in other words, you have a lens, you like kind of cut off the light, only keep the light that's going through the middle and let it fall on the lens. So you see a big spot. The smaller you make the aperture, the bigger you make this, so it will become bigger. So let me try to erase that and draw it again. So basically it will become, so the smaller you make this like region where you let light through, the bigger it will be. On the other hand, if you make it the hole bigger and bigger, so that it complete, like, so the entire lens is like kind of, you allow light to go through, this becomes narrow and as narrow as you can possibly make. Why is this important? This width of this the 2D sinc function is basically your resolution. So the resolution of a microscope is determined by how much of light the lens is letting through, what angles of light. So if it lets in the high angles, if it lets in all the angles like from the edges, then you will get a very tiny spot and you will get very good resolution. If you only let light in the middle go through, you cut off this large angles and only keep the small angles, then you see a very big spot and you will see a worse resolution. So this like how much of light goes through the lens is a crucial parameter which determines the nature of the what you see. So if you, instead of this being a dot, if you have any object, then the object that you will see is basically a convolution of this point. This is the this is the sinc function, convolution of the sinc function with the object. So basically, the reason why you have these in the very first slide, I showed you these edges, right? Let's say you have an object which looks like this red shape, which has these sharp edges, and like you look at it under the microscope. What the microscope does is takes the shape, convolves it with the sync function, the 2D sync function. And that is why this is the shape you get after you do the convolution of this shape with the the sync 2D sync function. Is this clear? Any questions about this? Okay, so this is the crucial, and so just like in signals in your signals class or anything before, this dot is a delta function, and so this is essentially like an impulse response of the optical system. It's a two-dimensional impulse response of the optical system. This is point, right? So this is also called the point spread function. So PSF. So the point spread function of a system tells you how good of a quality image you will get. So basically everything, like a dot will become a blur of this shape. Okay. So if you have multiple dots, so you have two dots next to each other, they will become two blurs of this sort. If the dots come very close to each other, this blur and this blur will mix with each other. Imagine if these are very big, then they will not be, you can't resolve these two. But if these dots, the sync function width is very small, then you can easily resolve them. So basically this determines how good of what is the quality of your image you will see is determined by this point spread function. So essentially this is also like a transfer function. What this kind of an optical system does is two things. One is it does magnification. So if you have 1 over d1 and 1 over d2, if you remember, d2 divided by d1 is the magnification of your lens. Okay, so it magnifies the object and it blurs it. So the old classical ray optics will only see it magnifies the object. You have an object in an image. If you look at it under a microscope, the classical what you imagine is it magnifies and makes it look bigger. But the wave optics additionally tells you that it also blurs. There is a limit to which you can see this, and this is what's called like this is the blur of the as a consequence of the imaging system. And this is true of all kinds of imaging systems. This is not just true of like this is all anything to do with optics has this kind of an issue. And so this is what's called the diffraction limit. It's the limit to which the best possible case in which you can the best possible images you can get with this like a linear kind of a 4F or optical system is limited by the blur that is caused by the finite aperture. And in fact, if you look at a microscope or a lens, any lens will have what's called a numerical aperture or NA, which is, so if you take the lens and if you take the angle, half angle of this cone, and the n sin theta, if n is the refractive index, if it could be, it's mostly air where n equal to 1, but this could even be water or oil or something like that. And in that case, n sin theta is called the numerical aperture of your system. And this is what decides what angles of light go through, and therefore, the higher the NA, the better your resolution. The lower the NA, the worse your resolution. This is something which any lens or any kind of optical system that you build will have to, like, by knowing this numerical aperture, you can figure out how good quality, how good of a microscope it is, or how good of an imaging system it is. Yeah, so mathematically, this is the transfer function of the generalized pupil function. If the system is in focus, basically you have h of the transfer function of the optical system. So you have a object, you have an image. So you can think of it as an input signal and the output signal, and everything in between is the transfer function. So what the system does. So the transfer function is related to the generalized pupil function. So this is related to the aperture itself, and this quantity, which is, it has epsilon. So if you are in focus, then epsilon equal to 0. If you're not in focus, then you can figure out what the system does. So the other thing that this allows you to do is figure out if instead of being at the image plane, if you are slightly out of focus, then what is the image? What will the image look like? You take this transfer function, multiply it by the input in the Fourier domain, you get the output. You take the inverse Fourier transform, and that's the shape of the image you will see with your imaging system. Any questions? Okay. So before we break, the last thing I wanted to discuss was what's called near field imaging. So what I've told you so far is that with an optical imaging system, there is a limit to the resolution that you can see, and that's limited by the width of the sync function, or in width of the aperture of the size of your lens and the aperture of the lens, right? So the bigger the lens you use, so if you use a giant lens and focusing like relative to the object you're looking at, if you use a big lens, in other words, if you use a very high NA, you can see the smaller and smaller objects. And depending on it also depends, the resolution also depends on the wavelength of light. So rule of thumb is lambda by 2 NA. That's the resolution. It depends on the wavelength of light you use, and it depends on the numerical aperture of the lens you are using. Okay, so those are the two considerations. So this is called the diffraction limit of your imaging system. But what if you want to see things smaller? You could do that. So the way to do that is using what is called near field imaging. In other words, instead of actually building an imaging system, if you get so very, very close to it, so what do? You want to see, like, so the spot that you can see is this width, like this is a kind of, this is limit, this is what you can say. You have an object and you want to see a very small thing, but your light which is focused cannot focus to that small dot. It will focus to a blur on the object. What can you do? You can put a small pinhole, which is even smaller than this hole, right? So if you put a small pinhole, then the light that goes through the other side or through the pinhole will be even smaller. That is one way you can make the resolution better. But the disadvantage is you literally have to touch the object, almost touch the object. And you could destroy the object. Like in practically, you may not be able to do this, and you will get a very low signal and so on. There are other problems with it. But if you want, one way to kind of get around this kind of diffraction problem is that you put a very small tiny hole very close to the object, and then that is kind of this is the field of near field imaging. I won't get into it in today's class, but I just want to mention it so that, like, there are some ways of getting around this problem, but for the most part, like 99% of the imaging system microscopes that you will see have the diffraction limit kind of a problem. Okay? So this is a good time to take a break. So the next topic I'll talk about is holography.